So a long time ago, Michael Faraday noticed that you could induce a voltage by changing the flux on something, depending on the number of loops, right? And then you wanted to change the flux as a function of time. So a changing magnetic field creates an electric field. And Maxwell, James Clerk Maxwell, now that guy was a thinker. And he was a mathematician, and he noticed that a lot of things are symmetric, like people's faces, you know? You've got one nose in the middle, and I can't draw the standard nose, so let's draw a cat nose or something, and the smile's like that, and you usually get an ear over here and an ear over here. Some people, no, but you know, you could part your hair on the side, but it's really best if you part your hair in the middle, because symmetry is a really powerful law of nature. And if you're going to grow a beard, you want to have the beard on both sides of your face, right? Otherwise, you look like you forgot to shave the other side of your face. Or forgot to grow out the first side of your face? I don't know. That's complicated. Anyway, don't do what that guy does, because symmetry is really powerful. What I'm saying is that if a changing magnetic field makes an electric field, and therefore a voltage, then perhaps a changing electric field can make a magnetic field. And Maxwell didn't do experiments, he just sat down and did a whole bunch of cool calculations. But later on, people did experiments. So I want to propose this to you right now. I want to propose that you've got an AC power source, and you hook it up to a wire and another wire, and then you go like this with the wires, and they don't go anywhere. What? Really? Yeah, they're just not going to go anywhere. Initially, you'll get a situation like this, where you've got some positive charges up here and some negative charges down here. And that's because of the AC generation. Now, we've got an electric field, right? And that electric field then points which way? I guess it points from the positive to the negative. There's our electric field. And then a moment later, we will get to the situation where it looks like this. I'm going to draw time this direction. And we've got our AC generator. I'm going to have to abbreviate this pretty soon. And we've got actually no electric field at all. But see, the funny thing about this electric field is it existed and it goes outward. Watch it. Here, this is the electric field, and it's going that direction. And it still exists, but it's just further away. This is going to be a little bit insane, but the electric field has gone to right there, and it's still, I mean, arguably has changed slightly, but not much, and it's just further away. And we've got no net charge on this guy in that instant. And sorry, we've got no, not even a polarized charge. And then our bearded man, half-bearded man, is going to be getting in the way soon, but we'll do this and say, still a moment later, we're going to have we're going to be switching these charges. We're going to have pluses down at the bottom. And then we're going to have an electric field that is then what? I guess the electric field points from positive to negative, and it'll be like that. But remember this electric field that we sent off at the beginning? We were like, whoop, go by electric field. It still exists, and it's over here now. So if you are watching, if this has been happening for a long time, then there's probably also an electric field that happened when the antenna, this is an antenna, right? When the antenna was putting the charges in the other orientation, and then over here, we could probably continue this on for quite a while and say, let me make that concrete for you. I'll give you a heck of a lot of these things. If it has been happening for a long time, they're switching back and forth, and this kind of, well, look at what's happening here. It's not like suddenly on, suddenly off. It's probably doing something like this. If we graph electric field as a function of location or distance away, we're probably going to be finding that, wait for it, we're going to have a big electric field now, and a small electric field now, and a big electric field now, a small electric field now, and a big electric field, and a small electric field, and a big electric field, and a small electric field. Okay, this is a wave. We've got a wave of electric fields, but at the instant, see, that's all well and good, but at the same time, this is an electric field, at the same time, we've got essentially a current in this wire. Now that's a little bit strange because of diarrhea, because we don't actually have a circuit here. We've just got a wire floating up into the sky and another wire that's going down a little bit. And we could definitely argue that since we're sloshing the charges back and forth, we've got a current. And at the instant that we've got a current, let's see, which way is the current now? Somehow that current went down in order to make the, oh man. First of all, let's identify the direction of that wave. The wave is going that direction. That's the direction of propagation. And the electric field at this instant is up. And I'm going to argue, let's see, I'm going to argue that the magnetic field has to be up. I'm sorry, I'm doing a bunch of calculations in my head. That in order to get these charges this direction, we have to have a current going down. Wouldn't you agree that the current is going down at that instant? That's how we got the electric field that direction, because the current was that. I mean, this is a little bit counterintuitive. I kind of feel like I'm waving my hands. But if the current's going down, then there's a magnetic field because of this effective current. And that magnetic field, what color should I use for that? Orange. There's a magnetic field because of this current in the antenna. And the magnetic field at that instant over on this side points out. I guess if the current's going up, though, that would be what happened in order to make the electric field distributed like this. If the current went up, it made an electric field distributed like that. And in that case, if the current's going up over to the right of the wire, then we'd have a magnetic field pointing in. So at the same time as we've got electric field pointing up, we've got magnetic field pointing out. Let me draw all of those. These are magnetic fields. And here's another one. And then at the same time as we've got electric field pointing down, we've got magnetic field pointing into the page. And if we make a cross product, we say that the direction of the velocity is the direction of the electric field crossed into the magnetic field. So at that instant right there, that says that the velocity is to the right. You will find that always, the electric field and the magnetic field are at right angles to each other. I suppose you're not too surprised at that, because electric fields and magnetic fields certainly do have kind of a normal to each other kind of flavor. They're very much different from each other, and they have to be at right angles. But the cool thing is that there's an electric field at the same time there's a magnetic field. And when the electric field is gone, so also is the magnetic field. And this pissed me off a little bit. But here's what I'm going to do. I'm going to try to draw this. First of all, I'm going to make some little green crosshatches up and down so that we can visualize this guy a little bit better. You are perhaps wondering why I'm wasting so much time with electric and magnetic fields. This is light, people. This is freaking light. So if you want to know why you can see stuff and why stuff cools off when you put it outside, I mean, like all kinds of things. If you want to understand stuff, you've got to understand light. So that's why we're going into so much detail on this. Now I'm going to draw you a magnetic field, and I think I'm going to have to use orange for that. The cool thing is the magnetic field comes out like this, and it's at a 90 degrees, so I'm trying to draw it like out of the page, like. You kind of with me? So it's like this, and like that, and like this. Like that. Now it's out, and now it's back in, and now it's out, and now it's back in. And so it's this direction into the page, and here it's out of the page, and here it's into the page. What? Is that right? No, out of the page, into the page, out of the page, into the page, out of the page, into the page, out of the page, into the page. Ah, good. So you've got this oscillating electric field and you've got an oscillating magnetic field, and they both happen as a function of time, and they move away from the source. In fact, what I need you to know about light is that every time a charge accelerates, every accelerated charge radiates light. That's cool. The next thing that I want to tell you is that if this wave happened to bump into something that looks like this, something beautiful would happen. Watch this. I'm going to have this wave coming in. Here we go. Check this out. I'm going to have this wave coming in to a wire that just happens to be hooked up like this. There's a wire here and a wire here, and I'm going to open this up into a circuit where I've got myself a capacitor and I suppose an inductor. Yeah, okay, I'm with you. And maybe I can change the value of this capacitor. I'm going to call it a variable capacitor as a result. Variable capacitor, and here I've got an inductor, and maybe that inductor is hanging out with some other part of this. Wait a second, hang on. As this wave, this oscillating electric and magnetic field hits those wires, it will cause the electrons in this circuit to slosh back and forth. It's an electric field hitting this thing right here, and I'm going to call this thing right here, is called an antenna. And that sucker is designed to shake well. In fact, look how similar it looks to this other thing over here. This guy right here is a broadcasting antenna. Oh, here's a better picture of it. We've got a broadcasting antenna here. And over here we've got a receiving antenna. And dang, if they're exactly the same shape, then everybody wins. What? This guy can talk to that guy across many, many kilometers. Yay! So we create a pattern of oscillating electric and magnetic fields. Field goes up, field goes down, etc. At a certain frequency. We could define an omega for this. And then if this radio, this is a radio, if this radio is tuned to the same frequency because of this, what are you going to say? You're going to say that the resonant frequency is something like the square root of L over C or something like that. If it's tuned to the same frequency, then we're going to get this thing sloshing back and forth in the same way as the original broadcasting frequency was sloshing back and forth. And now this guy can communicate with that guy. I probably also want to hook this up to another solenoid. There we go. And this is going to be going to the amplifier. And this is sort of similar to my electric guitar pickup coil communications. Now instead of sending a signal from, oh man, all kinds of complicated stuff, to an amplifier, we're just going to take a signal from this little circuit connected to an antenna to the amplifier, and we have been able to communicate across a great distance. In fact, the speed of light is really fast, and that's really handy. So I'm going to say that the speed of light is actually 2,99792. You might as well memorize this. 458 meters per second. This defines distance now. Yeah, that's really precise. In fact, infinitely precise, because the speed of light defines the length of a meter. A meter is the amount of distance that light goes in a vacuum if, let's see, speed in vacuum. It's very important to note that that's the speed in the vacuum. The, well, it's the speed of, it's the distance, sorry, 1 meter is the distance that light goes in that fraction of a second, 1 over that business right there. So the cool thing is, if light wants to go all across the great country of Slovakia, here it is. So this is about 450 kilometers. If light wants to get all the way across the great country of Slovakia, I did the math. It's going to take 0.0015 seconds. Dang! That's a little bit over a millisecond. So you can have a radio channel over here broadcasting an antenna, broadcasting a radio signal, and the people over on the left side of Slovakia, west side, are going to hear that signal less than a 100th of a second later. In fact, just a little bit over 1,000th of a second later. So if you're looking for, oh man, wow, we could talk about satellite lag when you're communicating via satellite, because that's a little bit longer of a distance. But if you're talking about the United States is about, oh gosh, it's about 4,800 kilometers across. And so to communicate from New York over here to San Francisco over here takes about 0.016 seconds. Light is really, really fast. In fact, you remember the speed of sound? Speed of sound was something like 330 meters per second, and the speed of light is something like 300 million meters per second. Yep, that's just about 1,000,000 times faster than sound. That's it. Light's cool. Mathematician, and he noticed that a lot of things are symmetric, like people's faces, you know? You've got one nose in the middle, and I can't draw the standard nose, so let's draw a cat nose or something, and the smile's like that, and you usually get an ear over here and an ear over here. Some people, no, but you know, you could part your hair on the side, but it's really best if you part your hair in the middle because symmetry is a really powerful law of nature. And if you're going to grow a beard, you want to have the beard on both. Initially, you'll get a situation like this, where you've got some positive charges up here and some negative charges down here. And that's because of the AC generation. Now, we've got an electric field, right? And that electric field then points which way? I guess it points from the positive to the negative. There's our electric field. And then a moment later, we will get to the situation where magnetic field. And Maxwell didn't do experiments. He just sat down and did a whole bunch of cool calculations. But later on, people did experiments. So I want to propose this to you right now. I want to propose that you've got an AC power source, and you hook it up to a wire and another wire, and then you go like this with the wires, and they don't go anywhere. What? Really? Yeah, they're just not going to go anywhere. So a long time ago, Michael Faraday noticed that you could induce a voltage by changing the flux on something, depending on the number of loops, right? And then you wanted to change the flux as a function of time. So a changing magnetic field creates an electric field. And Maxwell, James Clerk Maxwell, now that guy was a thinker. And he was on both sides of your face, right? Otherwise, you look like you forgot to shave the other side of your face. Or forgot to grow out the first side of your face? I don't know. That's complicated. Anyway, don't do what that guy does because symmetry is really powerful. What I'm saying is that if a changing magnetic field makes an electric field, and therefore a voltage, then perhaps a changing electric field can make a